To be presented by Duc Tran.
Thank you, John, for the invitation to this workshop. Very interesting that so far we have very diverse presentations, and I'm honored to be part of this interesting workshop.
You put the mic closer to the little thing here.
Hello. So I did this work when I was at UNM, working in the group of professors Sulsky and Schreyer. It has been more than 3 years ago, and one of the bad things that I have is my memory. So usually I forget quickly what I stop working on that. So I try my best to give you all of I remember about this work. So the overall project is about the modeling of the dynamics and thermodynamics of sea ice in the Arctic Ocean. Try to answer those questions. And our models, I mean the ice model in this project is coupled with the ocean model developed by the people at JPL. What I mean coupled means that the two models run at the same time, and the data exchange between the two models happens at the real time of running. So it's a parallel code. As the people, Kara also mentioned that in the Arctic Ocean sea ice, the leaks are very important feature because of they are the source of new ice forming during the winter time. And then under the load of wind and ocean currents, then the pack ice moves and they force the new ice forming in lakes into ridges or down into keels. And so besides modeling the dynamics and thermodynamics of the sea ice, in this project we also focus on the development of the constitutive model to take into account of the existence of lakes and ridges, etc. And as a small part of this project, that I wanted to have a specific constitutive model that can reflect the existence of open water, thin ice, thick ice through a variation of thickness. And that reflection could be anisotropically. So I will, and that is the main part of this presentation. So I'm going to talk about a little bit about the background of the project, and most of the background are already mentioned in Kara's presentation. So I will not go into details. Just to remind you that because usually the thickness of the ice varies from 0 to several meters in average, can be 10 meters in ridges, but compared to the size of the computational domain, which is the Arctic Ocean, then several meters is nothing compared to thousands of kilometers. So all of the government equation reduced to two-dimensional description with the plane stress condition is assumed. In this equation, as also already Kara mentioned, that N is stress integrated over the height of the pack ice, and the other terms are just the loadings in terms of wind, ocean current, and Coriolis force. Then because usually a computational element could be 5 to 10 kilometers each side, so within that area we have to take into account the thickness is vary from can be 0 to several meters, and people usually use a thickness distribution function. G by definition is a ratio between the areas, where AI is the area that has the thickness vary from HI to HI plus 1. Then the governing equation for the thickness distribution is this equation, and then the stress, integrated stress related to thickness distribution through this integral, where sigma is the real stress, and then multiply with the height. If sigma doesn't depend on thickness, then this integral simply becomes a multiplication of h and sigma. But sigma does depends on h, and in this sense we want to incorporate this dependence of stress on the thickness into n, and that's our purpose, our motivation. As I said, that we need a distribution of thickness function G to represent the variation of thickness within the computational cells. And for numerical implementation, usually we approximate, we discretize the thickness distribution into a finite number of categories, and associated with each category is the thickness and the fractional area. And on the background of those finite categories, the thickness distribution function is solved approximately, and then to get the result are the fractional areas. And then based on HI and AI of each thickness distribution, I will incorporate those data into a constitutive model so that we can reflect the variation of thickness. Okay, so let me try to explain a little bit about the purpose, the concept, basic concept. So suppose, for simplicity, I have an element of two categories with two thicknesses and the dimension of each category. So the purpose is I want to replace this original element by an equivalent element, but it has a uniform thickness. So this idea is analogous to an elementary problem of the spring. So depends on how the springs connected to each other, we can see that the stiffness of the system is totally different. When the spring connected in zero mode, we all know that the stiffness of the system is a harmonic mean of the stiffness of each member, and also for if they connected in parallel, then it's a limited mean. So let's look at from this picture to this picture. You can recognize that, okay, if I pull in horizontal direction, then this element looks like a two spring connected in serial mode. But if I have a loading in vertical direction, then it looks like a two spring connected in parallel mode. But it's not that too simple, because if we do like that, it just separate of the two 1D problems. But this is 2D problem, means that they have the Poisson effect on the system also. Also, because at the beginning I said, okay, we want to represent the open water within the cell. For example, and you know that the open water doesn't have any strength in terms of tension or compression, in terms of tension. So, for example, one of the springs are broken, then the system completely, this serial system completely doesn't work completely, right? But even for this system, even one of the spring is broken, then I still have some strength of the system. That's why I say, okay, for one element, if we have open water, it doesn't mean that that element is out of work. Right? Okay, so that now I go to a little bit about detail of what we did. So the purpose is trying to replace the element that has a thickness distribution with the data Hi and Ai are known, are given, and also the orientation of the thickness also is given. Then the purpose is to replace this original element by an equivalent element that has a uniform thickness. The principle, the idea behind how to replace it, well, we say under the same loadings, the deformation of the two elements, the original element and the equivalent element, have to be the same. How to do that? Well, in composite material, people are already familiar with the rule of mixture that it calculates the property of the mixture of materials. So we're going to use the rule of mixture model to derive the moduli and also the Young the Poisson ratio and also the shear moduli of an anisotropic material. Okay, I'm not gonna go into detail of the mathematics, so I just show the ideas and the final result. So, in a small scale, we assume sea ice is isotropic material with the properties of Young modulus and Poisson ratio. But that is if we go to larger scale, that an element usually very big, then based on the concept that I already mentioned, that it will behave like an anisotropic material. And so then we use the rule of mixture and to calculate based on the principle that we say, okay, the deformation of the two systems have to be the same under the same loading. The only thing different is instead of having different thicknesses, then I have a uniform thickness. Etc. I don't go into detail of the mathematics of calculation. Then the final result is that, okay, the Young modulus in one direction means that the direction perpendicular to the orientation of the thickness depends on the distribution of the thickness, and also depends on the dimension of each category. You can see that in here, if one of the thickness, for example H1, goes to 0, means open water, then in direction 1, that it doesn't have the strength. So E1 will be 0. So that at least at the beginning, at now we say, okay, this result maybe it looks reasonable. Now we go to the model for E2, means that the Young modulus in two directions, that is parallel to the orientation of the thickness. And we send the same rule of mixture, and then and finally we got that okay, the Young modulus in two directions is exactly the same as the Young modulus of the material. By the way, HP is calculated based on the conservation of volume. So we replace this element by this element, but we have to conserve the volume, so we don't lose the material. That's why HP is calculated very beginning. That's now I'm gonna go to the models for Poisson ratio. As I said, that this is not only the two problems of 1D, it is 2D problem. So not only the pulling in two separate directions, but also it has some Poisson effect. That's why we need to care about okay, how the shear deformation looks like, and that's why based on that we calculate the Poisson ratio when I pull in two directions, and then it's deformation in one direction. So then I came up with the Poisson ratio exactly equal to the original property. Also for the shear modulus in 1-2 direction, and the final result is here. And you can see that also here similar to the result of E1, I mean the moduli in one direction. If one of the thicknesses, for example H1 goes to 0, then I don't have shear modulus, because see, if this is open water, then how can this element can sustain from the shear deformation? Okay, so after derivation of all of the properties, then we came up with the final result. So I just summarize here that it can be expressed in terms of the two nominal thickness H S represent for serial and P for parallel, means that two springs are connected in serial and parallel mode. And then E1 depends on this ratio, and HS and SP are just arithmetic and harmonic means of the thickness. Those derivations are based on the simplest case of two categories, but the result is straightforwardly extended to the case of multiple categories. Just a little bit complicated formula for calculating HP and HS, but the remaining are basically the same. Then I can put the constitutive relation, I mean the relation between stress and strain, into a matrix form. Look familiar with mechanics, epsilon in terms of sigma. But now I don't say E1 or E2, but you can see that instead of E1 and E2, I say E and N, that are the properties of the isotropic ice material, and it depends on the ratio K. K is the ratio of HS and HP, etc. Okay, so that's for the elastic stage. Now means that if the ice deform still in elastic regime. Now we go to model the failure, and as I said, it's also very familiar with and similar to what Kara already mentioned, that we use a decohesive, elastic decohesive failure model that analogous to plastic theory. We define what we call it decohesion function. It looks like a plastic yield function, and we include all of the properties of the material. For example, tau and F is strength of the material in tension, and also tau SF in shear, and sigma TT FC is compression in this relation to take into account of the failure in compression, axial splitting, etc. And like I said, analogous to plasticity, we say, okay, in order to have the initial failure, F has to be equal to 0, and if F is not than 0, then it's still in elastic regime, etc. And we also in this model, we not only predict the initial failure, but also we predict the direction of the failure surface indicated by the normal n. And a little bit different with the model that Kara and Buck did, that now instead of just looking on of the direction in plane, now I say, okay, why not is our plane? So not only the angle theta, but also the our plane angle phi, so that the failure surface can be our plane. Even this is a 2D problem because of the anisotropic sense. Okay, so just for continuity of the idea, so I just plot for the case of isotropic first, then later I will compare with the anisotropics to make it more sense. For the anisotropic surface, well, it looks like very similar to what Kara showed, but the only thing is now I have the two boundaries here. Okay, because for this regime we have two principal stress, compressive stress, and now the failure surface is our plane. It means it's parallel to the plane. So it's gonna be broken. So the normal to the failure surface for this region, you can see I show here a dot, means that the vector n is normal to the plane. But it's not for the case of when I have the principal stress here. One of principal stress is extension. For example, here sigma 2 is positive, so the normal to the failure surface is in the direction of a maximum principal stress, and also here it's always in the direction of the maximum principal stress. But here the maximum principal stress is 0 because we have plane stress condition. So sigma 1 and sigma 2, both of them are negative. But remember, I have 0 stress in out of plane, sigma 3, and that is becomes the maximum principal stress. That's why now the normal and is here. Well, I say, how can this happens? Maybe I think under compression, this one can the failure surface is here, then this one can be broken like this, and this one. So it may explain why we have the ridges created as a layers of the ice sheets, like one picture I show in previous day of how the ridge created. So I think maybe can use this one to explain why the ridge created. And by changing the parameter of the strength, then we can have different envelope, etc. So that is just a feature of our model. Now we said that not only the stress is the anisotropic behavior, deformation behavior, but also now based on that we say, okay, the strength of the material now also depends on the thickness distribution, and that is makes sense, because for example, if you say, okay, when we work into the anisotropic model, if we keep tau and f as the strength in tension, then it doesn't make sense when one of the category becomes open water. Like I said, if it becomes open water, then if I pull in one direction, then the element cannot cannot be sustainable. That's why I have to include the dependence of the thickness distribution into the property, I mean the strength of the material. And also we based on the rules of mixture, and we can derive the strength of the material of this virtual or equivalent element in terms of the thickness distribution. And also we have this one in one direction, and it's also the two direction, and also for the shear strength and the compression strength. And those kind of the strength in principal direction. But now what about the strength in an arbitrary direction? Then so those are the principal direction. Then in arbitrary direction, then we say, okay, we just assume a tensor operation that in an arbitrary direction, and we say the strength in that direction depends on the basics strength in the principal direction by having this operator in terms of tensor. In terms of phi and theta, we can write tau n in this formula. Then now having those strengths in principal direction, and also a formula to calculate the strength in an arbitrary direction, then I'm now ready to have an anisotropic envelope for the failure, initial failure. And for example, with this I think this picture already hidden here, so I think it's tau ns here. Sorry for that typo. So the green is the envelope for the anisotropic case, and the pink is for isotropic. So you can see that now the curve is not symmetric at all, because for example H1 and H2, H1 is smaller than H2, so it's weaker in one direction, but in two direction it's still okay. That's why the envelope is kind of narrow in direction 1. And also by changing the distribution of thickness, keeping the average value of the thickness is 2. For example, H1 3, H2 1, so the average is 2. And now I increase H1 3.5, and so I decrease H2 into 0.5, but the average is still 2. Then you can see that now my envelopes of failure becomes narrower, narrower, narrower. And now once you can see if one of the thickness becomes approaches to 0, then this envelope becomes a line, so it doesn't have any strength in one direction, etc. So that's the initial failure of the how to calculate the failure at initial. But then because our model is elastic-decohesive, means that once it reaches to the initial failure, then the failure continue to develop up to some point that is broken. And this one already introduced by Kara, U1, Un, and U2 is a softening function, it's a linear softening function, etc. And the displacement is discontinuity, and it can be represented by two components in normal direction and also in shear direction. And now we incorporate that softening function Fn into a decohesion function to represent the development, I mean the growing of the failure surface from initial state to the final state when Un reach to the value of U0. U0 can be found at meters. It's a huge crack. It's 5 millions of microcrack. And evolution of failure, we calculate decohesion. This is the algorithm. I just go very quickly. We calculate the decohesion strength, and then we, in this model, calculate the stress rate. But now you see, instead of isotropic relation, I have anisotropic relation. C11, C12, etc. That is moduli. For numerical example, we want to test how the model, the theoretical model works. So first we try to do some very simple problem that it, suppose I have a plate of ice, and the rest, most of the plates are uniform thickness, except this area has the distribution of thickness. That is H1, A1 and X2, A2. A is the fractional areas and H is the thickness. And then I fix one end and I pull in this end to see how this plate deforms overall. But also, in order to compare with the isotropic model, I create a region with a little bit weaker material with tau and f. It's just 0.9 of the tau and f of the remaining region. Then I pull in this one by apply a prescribed velocity v0 very slowly, and see what happens. And this is and we use MPM, material point method, to simulate this example, and you see that those dots are just material points. It doesn't have any physical meaning. It's just the point to represent the material in this numerical method. And I don't have the video to capture from the beginning to the end, but this is just the picture at the end of the simulation. That is, the color represents for the opening of the crack. So it from 0 to up to once the crack completely formed, it equals to U0. So this is the anisotropic model, and this is the result of the isotropic model. And you can see that because I have the weak material here in this region, that's why in the isotropic model, of course, the crack happens where the material is weaker than the rest of the structure. But it doesn't happen like that in anisotropic model. In anisotropic model, it happens, the crack is created where I have the thickness distribution. Well, why? Because H1 is 1 meter and H2 is 3 meter, means that, okay, in this region I have a thinner ice. And if we don't use the if we don't use the anisotropic model, then we can have a wrong result because we ignore the thin ice here. And that is one of the features of our developed model, that it can represent the existence of thin ice in overall. And also we do some simple example to see this the softening behavior. So this is for anisotropic model and this is for isotropic model, and you can see that once at first the force, the graph is chart is a force versus displacement. Force, I apply a force here, and also I measure the displacement here. Then the force increase from 0 up to a maximum value when the crack start to be created. I mean the initial failure. And then after that, if we keep increase the displacement, the force decrease to represent the softening. The difference between the two models now is because of the thin ice exists in this region. That's why the maximum value of the force of this isotropic model is smaller than the isotropic model. And that makes sense because of the thin ice. We cannot, the thin ice will, of course, when we pull a structure that have thin ice there, then the thin ice will cover most of the force, and the crack will occurs first at the thin ice. And also the fracture energy of the two models are also different. It's an area under the curve. Now we see, okay, now the same example, but now I instead of the orientation of the thickness in vertical direction, now I just say, okay, same thing, same distribution, but the orientation is perpendicular to, is parallel to the direction of the loading, to see, okay, how does it work, how does the effect of the thin ice in this case. And you can imagine that it doesn't change at all, because in this case, even I have thin ice here, H1 is just 1 meter compared to H2 is 3 meter, but it's parallelly, it's in parallel direction, so it looks like two spin in parallel, so the overall strength of the structure is the same. And that is represented in the numerical result, that the crack still occurs in the region of the weak material. So it's no different between the isotropic and anisotropic models. Yes?
The cross-hatch area, can you explain again?
This area, I say, okay, most of the entire structure has the strength of tau and F, except this area has tau and F is just 0.9, so a little bit smaller, so that I want to have the crack happens there for numerical purpose. Okay, that is for the tension, but now I go to one example to test how the shear, how the crack appears in the shear mode. So I have a square region of ice, and I apply a wind force in vertical direction, and similar to the example 1, now I have a region of thickness distribution of two categories. One is thin and one is thicker, and then I fix on one side and then do the simulation, and then the final result for anisotropic model compared to the isotropic model, that you can see now for anisotropic model the crack happens where I have thin ice, but it's not for the case of isotropic model. For isotropic model, it doesn't see any difference. So it doesn't take into account of the existence of the thin ice, and that is a feature of our development anisotropic model. Okay, so that to be concluded, that we have developed a constitutive model that can model the ice deformation taking into account of the existence of thin ice, and also not only thin ice but open water, etc. So it doesn't, it's open water can be included, and determine the material strength accurately in prediction of failure. And numerical examples show that the feature of the developed model being capable of dependence of mechanical behavior, etc. So, well, this is just the theoretical development, and I know that we need to test it in reality. So we have to implement this model into a simulation to validate the result. And unfortunately, that once I've finished this development, then I have to leave the project, and I don't know if the next person is already implement this model into the simulation of the overall project yet, but I hope I can have some time come back to apply this model into a real simulation of the Arctic Ocean sea ice in the Arctic Ocean. Thank you.
Questions? It seems, just by looking at the numbers, you've got 70 kilometers by 30 kilometers, and somehow you, with the work over the years, you've worked out that, and you've got the softening model, and you put in 3,000 meters for U0.
Mm-hmm.
So do you remember how it was decided that softening function, that it was necessary to be of that order?
You mean how to decide the value of U0 or the design?
Of U0, yes.
U0. That's a good question, and that question we discussed many times when I was working in that group. Well, the U0, with what we did is we just assume that some values of U0, because we don't have any experiment result, and run the simulation and see if the simulation agrees with the observation, and then we think that U0 is the correct, at least a good one. And if it doesn't, then we change the value. I mean, the value of U0.
It must have been compared with something, like maybe another code, perhaps? Do you know how U0 was got?
So I think there wasn't a lot of there wasn't a good way to compare it. If you have a very small U0, it's essentially setting it to 0. So it's essentially turning off the cohesive part of the constitutive model. So it needs to be, if you have large cell sizes, it needs to be something fairly large for you to have, in order to have the effect of the cohesive property.
You see, no matter what, somehow, you've essentially worked out how much cracking would go on. By whatever means, you've worked out how much would go on.
Yeah.
And that's really interesting. So I wish it was written up.
Yeah.
How did you deduce that? Just to give, for those of you that don't know, if you go and do a fracture test in the Arctic in, say, 1993, I tested a range of sizes, and we worked out that for a crack in a 2-meter thick ice sheet, sea ice sheet roughly minus 15 degrees C, a crack is essentially fully established once it's 40 microns thick. So to have 3,000 meters here in a far different setting, of course, 70 kilometers by 30 kilometers, it's a summary of all the cracking. So it's very interesting. So you say that if you would like to come back to this, one really important topic is to let the rest of us know how you deduced what was physically needed. But in a way, it has an interesting result, because I think it tells us to get reasonable results with your particular model. Now again, it's the Schreyer model has been accepted in other contexts, so it's not unpopular. It's getting used at different scales. But the attainment of that value of U0 is of significant interest.
Well, I think that in terms of the how to decide, how to determine the U0, I think one of the ideas is to look at the fracture energy, because as I show in this okay, then so once the crack completely created, so when displacement equals to U0, then the area under this curve is the energy of the fracture. So it's related to U0. If we know that in terms of material science that we can somehow we can calculate the energy required to create crack in sea ice, then we can say, okay, we have energy, then we have relation between energy and Z0, and we can get the data for Z0. But the problem is, how do I get the fracture energy of?
I suspect other means were used to get U0. It was other phenomena that had to work out, and maybe it was based on observations or cases studied by previous workers. Because I know that the kind of scenario you're showing, Bob Pritchard way back worked out several scenarios. So, but anyway, do we have any other questions? Okay, well, let's thank the speaker again.